Hi, I'm going to show you how to build a process simulation model using Aspen Plus. I'm using now Aspen Plus version 12.1. So we're going to quickly develop a process simulation for a simple DME flow diagram. So for example, in this case, so we have methanol coming in with 10 tons an hour of methanol stream. It consists of 99.5% methanol and 0.05 weight% of water. It goes to this vessel, and then from this vessel is pumped until about 15 and a half bar gauge through this heat exchanger, and then we have a heater to make sure that the inlet temperature to the reactor is about 250 degrees C, and then in this reactor we simply model it like in a simple conversion reactor model, um, where the methanol is dehydrated to make DME in these reactions. And then the outlet of the reactions is split to make sure that it can be cooled down or to maximize the amount of heat as much as possible to be transferred to the feed. And then in the end, it will then be cooled down to about 100 degrees C and then expanded to the column pressure of about 10 bar gauge. This is it has 24 stages, the feed coming at stage number 12. Um, full liquid condensation of the top product DME. So these reactions, because it's 80% conversions, so that means 80% of methanol is converted. That leaves 20% of methanol in it. So what is coming out of the reactor is about 20% of methanol, and then about 40% of DME and water. And then the DME, being the lightest, gets removed in the first column in the top section, and then the water and methanol, unreacted methanol, goes to the second reactor, where the methanol being the lighter than the water, so it is sent back um, to um, to uh, to the original vessel, while the wastewater is then the water is then sent to the wastewater treatment plant. So we'll be showing you how to use Aspen Plus to model this very simple flow sheet. We go back to the Aspen Plus, open this, and we create new. So we can either use a template or start from scratch. So we will then use a template in this case. So I like to use, like, for example, metric, and then the chemicals with metric units. We need to it will, by default, it will go to these units, but then we can always change. Yeah. Um, now we can select the component. We can so this page is about the selecting the components, properties, and so on and so forth. And then the simulation page is on the, and if we click on this button on this page, it will be directed to the simulation page. But we cannot proceed on this unless we key in the components. So the components is over here. So we click find, and then we can either write begin with or contains or equal to, in this case we know for sure our chemical, so we begin with, for example, in this case methanol. um, Methanol, yeah, so methanol, enter. It begins with the methanol over here, so we can need to only we want to have only like methanol. Click add, and then we add into it dimethyl ether. Not ethylene glycol, but we need to have dimethyl ether, for example, maybe in this case this one, the C2H6O, dimethyl ether, add, and then we want to add, not to replace, and then click yes to update the parameters in the current NRTL model as shown before, and then water, and then we need only this water add. So we have everything there is, so we can rename this F2 methanol. I want to rename only, and then this is then DME. rename only. So now we have selected the components. Now we go to the method where we have to select the property package. So in this case, the default for this chemical template is by NRTL. Uh, in this regard, we would like to select the UNIFAC. So the UNIFAC, and then when we selected the UNIFAC, and then these are then the things by default. We can modify it, but it will be in a different class. And then if we see that there is this white and red, that means there's something is missing. So we can just, in this case, by clicking what is there, what is missing, by clicking what is missing, it is automatically filled from the database of Aspen PLUS. So in our case, we are not using the NRTL, we will be using the UNIFAC. Later on, we can compare. Yeah? So once we have selected once we have defined the component and then the thermodynamic model, we go to the simulation, and then we will then add the materials. So this is then this is the user interface of Aspen PLUS, a little bit more with a look like ISIS now. Material, so we can just click and then click once again. So we have click once and then click or double click directly in this case. So to the cursor is being like, if we click another one, we'll have another stream coming out. So it's right click is then to remove it. So this one we don't want to have it. Click delete. Double click to enter the stream. So we know that it's 10%, 10 tons an hour. So 10 tons an hour, and the mole fraction is 99.5% of methanol, and the rest being water at 0.05. It's coming at yeah, atmospheric maybe 1.2 bar, and then like 30 degrees C, for example. So we have entered, and then you can see it's blue, so it means we can run this. Aspen PLUS is the way to run this. We can just click next, but in this case we need to connect this to a unit operation. So for example, we can connect this to a vessel, because it will enter the this vessel anyway. So I think I can make it like a next to each other. Yeah. Yeah. So you enter this vessel. You can then say vessels. This class special, you can then yeah, take whatever you want by clicking this, and in here we just click there. We can rename this. We can rename this with a right click and then rename. For example, in this case V01, and then we can double click on the edge of this stream so that it can be you will then see this sign, and then by which you can then connect it, or you can then directly goes to this, and then we'll see. No, there is no connection. So this vessel, it operates like a, well, we can see that this vessel operates adiabatically. So in this case, there's no heat coming in or out from the system. So and then there's no pressure drop. So there's no pressure drop. That means we can then I think if you hover this, and then you will see there's no pressure drop. That means the value is then at least 0. So it's 0, no pressure drop, and then there's no heat being transferred in and out. So we can then select temperature duty instead of temperature. So there's no heat coming in and out. So 0, and then we close this, and then we need to add some more streams. Otherwise, it will not be we cannot run this. Click on the vapor and another one on the liquid. This one is yeah, if we have for free water or dirty water. This one is for the bottom. Yeah. Okay. So once everything is there, we have the inputs. We feed the inputs into this stream, and then the input data, and then the unit operation data we feed it there, and then hence there is this run button active. Yeah? So we can then click next. We can either click next or click run. I want to show you something. Click next. You click next, and then it will then say all required input is complete, and then you can run the simulation now, and then you can click OK. So once you click OK, it will then show you control panel, and then it will then tell you it is now processing input specifications, and then it is now computing the VO1. This unit VO1, it is then computing the VO1. Yeah, so you compute the VO1, which then using the model flash 2, and then no error, nothing, so it's all good. You can see what the outlet is. If you go to the VO1, you can see the stream results, and you can see there is no stream. Number 3 is stream vapor stream, number 4 is then the liquid stream. You can see liquid phase, vapor phase. There's nothing in the vapor phase because the inlet is at this methanol at this condition is liquid. Okay, so now once we have this vessel, we want to recycle. We can add later. Yeah, I will show you how. We'll then can add pump. So pump is then the pressure changes. So we can add pump. Click on it and then click it again, and then right click on the flow sheet to deactivate this pump. Double click and then connect it. Otherwise, if you can't click it, just right click and then reconnect destination, and then you can then connect it easily to the pump. And then this pump, we can have a discharge pressure of about that 14.5 bar or bar gauge. So we can put bar gauge for example, and then you can because this is blue, you can run this already, but we need to add. You need to add before you can run it. You need to add the outlet stream. Then this will be active. You could also add some efficiencies if you want, yeah. But in this case, we just keep it like by default. And click material stream product, which is required. You can see, and then this is then there. So we can run this and see what happens. So it's all blue and its results available, and then we can then rename this as P1. We can rerun that again to change the name. You can see now in this case, sorry, the PO1 so we are pumping and the difference pressure is 15.5, and then the pressure is 1.2 inlet, so 1.2 plus 15.5 is somewhere around this number. Yeah, so we can also say, okay, I want to have discharge pressure should be the outlet pressure of 15 and a half. Instead of 15 and a half, it gives us this 16.5, which is very strange. So you can then pressure increase by, for example, if it's 1.2 and then the 15.5 means about 13.3 14.3. Run, and we can see 15.5. Yeah. And this discharge pressure is in bar gauge. You can see it is in bar gauge, while it is being reported here is in bar absolute. Hence this 16.5 is then the bar absolute of the 15.5 bar gauge. That's how we look at it. And then to have it in bar, as you saw it, we need to put like this 14.3. And then once we get it, we can block it and then put it to the left if you want it. And then we can add this feed effluent heat exchanger. In this case, we can have the heat exchanger. We will need to use heat exchanger because it needs two streams. Yeah? And then double click, and then it is then the cold streams. So we need to put it there, not here, because this is hot stream. So cold streams, it needs to be heated, so it's cold streams. Yeah, it is set to it is named as cold streams because it needs to be heated, and then the outlet is then over there, right? So we can double click here. um, it's a shortcut design, so we need to do some specification. So how do we want to calculate that? For example, because we want to have it at now it's about 30 degrees C. Say for example we want to hit it like 150 degrees C over here, and then this heater will then take care at 25 to 250 degrees C. So if we say that this is 150 degrees C, we can then yeah, hot stream outlet temperature, for example, in this case we are now cold stream. So cold stream outlet temperature, in this case maybe at 150 degrees C, yes, for example. So once we enter this, this model then know how much then the heat being transferred from here to there, yeah, from the inlet to the outlet, because in inlet it knows the temperature, the outlet we just specify temperature, so it knows how much heat is going to be used. So once we, hence it is then blue. So then we cannot click next, because when we click next, we cannot run because it needs to have the hot in and out stream. So in this case we can provide like a dummy stream, assuming that this is 80% of methanol, sorry, 20% of methanol left, yeah. So we can have this dummy stream, hot required, and then so in this case we can have a dummy stream. We don't know what temperature here, but assume like this is exothermic temperature. This is exothermic reaction, so we could assume like 300 degrees C. And then yeah, assuming a pressure drop of half a bar over here, and also half a bar over there. So we have 15 and a half, 15, 14 and a half. That means this is then 14. So 14 bar gauge, 14 bar gauge, yeah. So in this case 14 bar gauge. The flow rate is still 10 tons an hour, and then the molar flow rates, because we know that methanol is only converted 80%, so that means 20% of methanol coming in is then uh, uh, still there, and then the rest 80% is then the mix of DME and water. And then in this case we can just assume, since it's like a dummy, it will be updated once we have the reactor connected. So this is 0.2 and 0.4. So now it is blue, and then you can run this. So you can run this, and then you can see the heat is stream results. So this is now can then click on this only. You can see thermal results, for example. Hot stream in stream number 2, out stream number 7 to 7, 5, 6 for the cold stream, and exchange this amount 1 gigacalorie per hour of heat. If we change it to the megawatt, for example, 1.2, or if it's like you want to see only like a kilowatt, it's 1200 kilowatt. the stream results, we need to have like so we don't want this, so we can then delete this one. We want to have 5 6 7, sorry, we need to have it 2. So 2 is then the inlet of the hot stream, and 7 is then outlet of the cold hot stream. So from 300 degrees C it goes down to 156, while in this case from 31 degrees C it goes up to 150 degrees C. Okay, so now this one, so 150 degrees C. We could also see if you don't want to click, you can see that we can click on this. It will then the value will then pop up in the on the flow sheet, and then we can also add like pressure so that we know it has this circle is then temperature, and this shape is then pressure. So how do we know that? If we press home, it will then show the whole flow sheet in one view, and then this legend is always there, so we can just simply drag it there so that then we can zoom in a little bit. So temperature is this, pressure is there with the corresponding unit, and then from here we can increase this to 250 degrees C by using a heater or fine heater or whatnot. Double click and then click another to add another outlet stream. This one you can rename, this one you can rename E08, and this one is E01. Double click. We can have another 250 degrees C, that's what we want. Pressure, because we will specify the pressure drop, so you can see if we hover on this, so if it's minus, that means that's a pressure drop. So we want to have it like a half a bar pressure drop. Enter, and then we can run this. Okay, now it's 250 degrees C, 16 not 16. So in this case because it's a 1 decimal point, we can go for we can click on this, and then you can see pressure, we can add 1 decimal point, and then enter, and then click OK. So you will see 16.5 bar absolute, 16 bar absolute. Yeah, if it's bar gauge, that means it's about 15 bar gauge. Now it goes to the reactor. So this reactor we simply use going to use a stoichiometric reactor. Use this for example. Put it there, and then put it outside, and then we can rename this R1, and then double click on the reactor. We want to run this adiabatically, so there is no heat going in and out, so this duty is 0. Pressure drop is we want to have it like a half pressure drop, half bar pressure drop, and then the reactions, go to the reactions because we need to specify this reaction. We click new. We want to have methanol. How much is the methanol? Because this is on the reactant side, so it's -2. And then this, then the DME, it's 1 DME, and then the water is also 1. Fractional conversion, so this is then where this number comes into picture. So 80%, for example, is then 0.8 or 80. We'll see later on 0.8 or 80. And then it's then based on the methanol, so 80% of methanol will be converted. Click next, and then it's all good, all blue, so we can run this. Yeah, we can run this, and then we will see the results. Balance, all balance stream results. I would like to see the stream results. So if we scroll down, and then mole flows, so now we have 300 kilomole per hour of methanol, and then 80% of that is converted. So what's left is about 60 kilomole, which is then 20% of this guy. And then according to the mole balance, so twice the number of this goes to the DME, and then the water as well. Yeah. the water is more than DME because we have water coming as the feed. We have water coming as the feed. As you can see in here, we have about um, about one and a half kilometer per hour of water. So 124 plus one and a half is about 126, 124 and a half, 126. So that's where the number comes from. So once we get this guy coming out of the reactor, then we can then, in this case, we split it. So if we want to split, um, so this flow sheet is now getting bigger, so we can then scroll it to get it magnified or minimized, make it smaller. Yeah. So in this case, we will have to split it, so we can then click splitter. Can use this one there. So double click and then put it there, and then we have two streams coming out. One is over there, the other one is over here. In this case, we can double click on the on the block. Sorry. Double click on that, and then we say, for example, we want to have the stream 11 is the one that is going to be connected over there. So we'll then remove the stream number 2 and then connect stream number 11. So we want to have, like, for example, I want to have like 80% or 90% or 90% of this stream going into stream 11. So 90% is about 0.9, right? So I cannot key in this number. I can only key in, I think I can key in this 0.9 now. 0.1 over here. Or is it not connected? Oh, sorry, value 0.1. So not basis 0.1. If I want to have it 0.9 over here, that can also be done. So we want to have a 90% to stream 11, and then we can then run this. So we have now 370 degrees C. Instead of 300 degrees C, we have it 370 degrees C. So obviously this stream brings a higher temperature, so it may bring more energy. So we can see how much is that the flow. The flow rate is about 9,000 tons. Well, in this case, it's 10,000 tons, I guess, because it's a full stream. Yeah, we assume it to be like a full stream, so 10,000. So we can then remove this and then reconnect that to this guy. So now in this case, if we click on the control panel, you can see the calculation assistant from vessel to pump to heat exchanger. See, vessels, so vessel to pump, heat exchanger, and then a reactor. So you can see vessels to pump, heat exchanger, and a reactor, and then the splitter. Can now run. Yeah, so you can see from here, because this stream is a recycle stream. In a way, it is a recycle stream. It's being calculated from this block, which comes from all of these blocks. So it's a recycle stream. So Aspen is now intuitively it will then tear stream 11, which then this stream, it will then tear stream 11. What it means is that it will then assume a number and put it over there, and then it will then use that number to calculate what is coming out over here, which is obviously it has been set. So 150 degrees C is then no matter what it has been then defined. Yeah, you can see it's defined over here. So this stream will not change because of this specification. So if this doesn't change and then everything else will not change, it's just a matter of adding this spec, the 90% that goes to this stream, and then what is being updated is only the outlet stream of stream 7. So you can see over here, so tear this stream, but then the computation order is then equals to v1 v1, so it goes to v1 v1, and then once it calculates v1, that means it has this stream number 5 already. So to calculate this, it needs stream number 11. So that's where this test stream coming from. So this stream 11 is calculated via this solver O1. So and then it goes to the exchanger 8. So this has been calculated by the P1. This has been calculated by the solver. It will then calculate the exchanger 8, and then it will then calculate exchanger 1, and then the reactor 1 is shown over here, and then the splitter. So it's there. Yeah, so that's how the calculation progresses in Aspen PLUS. So now once we get that, we can then mix this stream again, as in this case, before it is being cooled down to 100 degrees C in the cooler. So we have a mixer, so just put it there, and then this is then the double click over there, double click, connected over there. We have outlet stream. So we can just simply rerun this to calculate the inlet to the distillation column. So in this case, we can see it's about 165 degrees C. So we need to cool down to 100 degrees C via this cooler. So we have exchanger with cooler, this heater or cooler, depending on the specifications that we are inputting into the unit. Connected, and then it has a certain pressure drop, obviously. So a bar, for example, and then outlet temperature is about 100 degrees C. Run this, and you'll get what you want. Yeah. Now we have 15 bar, 100 degrees C, and then we need to expand this via this valve. So valve is then the pressure changer, so we can then click valve, the nicer one over here. Outlet pressure is about, yeah, if it's 10 bar gauge, so maybe we can have it like a 10.5 bar gauge or 10.5 bar gauge in this case. Right, so it will then calculate the valve parameter and so on. So results. See, it's not choking is not checked. Outlet temperature, outlet vapor pressure, outlet vapor fraction, and from here we can go to the column. We can use the shortcut or whatnot, but in this case we can use radfrac because we know already the specifications. In this case we forgot to rename this. This is going to be like a E2. This is then, we can enlarge this here, like that. D1, and then double click to connect it, and then we know that this is in this case DME is taken as a liquid. There is no vapor, so it is then total condensation. We can connect it first to liquid only, liquid distillate, and then the bottom stream. So this column we use equilibrium number of stages. We use 24 number of stages. A condenser is then total condensation, and then we can then now assume the distillate rate, how much we want to draw, here as the distillate rate, and then how much is then the reflux, so how much is then the reflux ratio. Yeah, see, this drawing over here is about recovery, and this reflux ratio is about the purity of the recovered DME. So we know in this stream, we know stream number 14, it contains example, 124.4 of DME. So we want to recover this DME as much as possible by increasing the reliability duty. So if we put more duty, all the lines, this DME lines, will be going up. But not only DME is going up, it's also water, and then the metal will go up. So in order to prevent that from happening, we are increasing the reflux. So reflux is then controlling the purity, the reliability, then controlling the recovery. We will do that later on. Yeah. So this lead rate, so we say that we want to have like 124 and a half, for example. Then the reflux ratio is 1, and then the stream is the feed stream is at 12. Above stage means if we have like a stage, this then stage, this then the tray, so it will then go into here. So the liquid part will drop on the tray surface, and then the vapor part of the feed, it will go up to the next tray. That's what it means by the above stage. We go to pressure. We specify the pressure condenser. It's about 10 bar gauge, for example. And then we run this. So once we run this, we can see the result, the stream summary. And this is the fit 89 degrees C. This is then the DME, the condensate, the distillate 48 degrees C. This is then the reboiler, the bottom stream 156 degrees C at this bar, absolute 11.5 or 11 bar. We can see the mole flows, so 124.848 484 for DME, and then there's some traces of methanol as expected, which is pretty good. So if we can see more fractions, about 99.99 of DME. We don't want to have this very pure. We do indeed want to get as much DME as possible. For example, we want to have it about 99.999, and the same with the purity of DME, 0.999. Let's see if we can do that. So we go to configurations, we go to specifications. We want to specify the design, so we specify the recovery and then we will recover the mass or the mole. It doesn't really matter. So target is at 0.099, and then you could put another line if you want. So what do we want to recover? The DME, obviously. In which stream? I think this is stream 15. Yeah, stream 15. There. So what do we do to do this? So we will then vary the reboiler duty, because the more reboiler duty we put, the more duty we put, the more energy we put, we will then maximize what is coming to the top. Maximize or increase. In this case, because if you can still see, we only use specification of distillate rate and reflux ratio. In this case, so we the derivable duty will be calculated indirectly. This simulation will then use the distillate rate as a handle to make sure that we recover the 99.9% of DME. So for that, we will then vary the distillate rate in this case. So distillate rate we vary from 0 until, because we know it's about this 120 something, so we just maximize it to be maybe 200, 150, doesn't really matter. So then we add another one for the purity. So we want to have it more purity, for example, 0.999. Component is in DME, where in this stream 15, obviously. And then how do we do that? We will then adjust the reflux ratio. example, until I don't know, maybe 2.5. Make sure that the value should be in between of this lower and upper bounds, otherwise we'll get the error. So we can run, and then we can see the results for the refractory ratio. For example, it was 1, but then now the value to achieve that, it reduces the refractory ratio to about half, and then the distillate rate is about, we can go to that amount of distillate rate, which is very much close to the flow rate of DME, as you recall. Okay, so once we do that, don't forget to save. Don't forget to save. Now we didn't do this is then DME is going to be sent as a product. So you can see as well, we want to see the mass flow rate, for example. Now DME is then 5733 out of 10,000 of kilogram an hour. So this one, it will then go to the second column. Front. It needs to be expanded as well because it's still 11 bar gauge. We need to have it like 7 bar gauge. So again, we put pressure changer valve and then put it there, connect it over here. So 7 bar gauge, for example. We cannot run this because we have incomplete unit. So if we delete this, and then this one we can run. Right, so and then we can add that column again. Rename V02. So we can enlarge this if you want. Double click on that there. Again, it's also like the total condensation of methanol, total condensation, and then the wastewater. So we know 28 stages fit at stage number 14. 28 stages. Condenser is also a total condenser. The distillate rate, we know how much water that is coming, how much methanol coming in. So we want to recover that as much as possible. So you can see mole flow is 62. Then maybe we want to recover 62 or 63. 62, for example, to make sure that there is no water back into the system, because this stream, the distillate stream, will be recovered back to the tank here, which is then going to be sent into the reactor and comes back to this tank. So if we have water going to the top, that means we'll have then accumulations of water in the system. We don't want that, or we want to prevent it, so we will then allow a little bit of methanol going to the wastewater stream. So hence we use 62 instead of that is 62 point something more. And the reflux ratio we can always adjust later on. So 1, and then stream is feed stage at 14, and then pressure is 7 bar gauge, and then we can run. So when we run, we see the results again. So both liquid phase, 130 degrees C at the top, 160 degrees C in the bottom, and then we can see the mole flows, for example. So we have methanol this amount, and then when we specify 62, water is also going to the top. Yeah, you can see not all water is not all DME is there. So let's see, now we want to make sure that we maximize the amount of methanol recovered and then minimize the water going to the top, which means we increase the purity of DME of the methanol. So we go to specifications, we go to design specifications, we can add, and then the recovery of methanol, the mole recovery 0.999, example, and then the component is then the methanol in the stream number 7, stream number 18, and then what we vary is the distillate rate, yeah, just distillate rate, distillate rate, and then you can say 0, 1 to, I don't know, 10,000, and then we add another. You just need to make sure that this, in regards of this lower and upper bound, we need to make sure that the solution should be in between these bounds. We want to increase purity of ethanol, or purity target. So in this case, we I don't know, we, because if we want to have it a higher purity, we need to put more reflux, means we need to increase the duty as well. So since this water is doesn't seem to be like very harmful to the catalyst and so on and so forth, so adding this into the system is not that bad. So if we say the target should be like 99, for example, it's not that very. So we allow like 1%, or maybe we allow like 5% of water into the methanol. So we methanol, and then this one is then there. We will then see, yeah. And then how do we do that? We adjust the flux ratio. From 0.1 until maybe, I don't know, maybe we make it maybe 20, and then we run this. So once we run this, it seems to be profile, sorry, not profile, stream results. You can see, so we have 95% of methanol, and then in the top, and then we are losing, so we make sure that 62, almost all methanol going back. We only allow like 0.06 kilomole per hour to the wastewater stream. So now we have done until here. Now it's the method. The final step is then to connect this stream back to the vessel. So the way to do that is that very simple. You can see it. So I can then remove it, put this there, so to make it very visible. So this guy, we can double click and then put it there, connected. So simple as that. And connect it. See, so it is now connected. It's now connected. So so everything here will be changed automatically. Yeah. So originally we have 10,000, goes up 10,000. So what goes to the reactor? So 10,000. But now with this additional 2,000 of the unreacted methanol, so we will then end up sending 12,000 of methanol more or less into the reactor. So that's a recycle. We can then click control panel first to see what's going to happen. We can clear it so that we can see. So now I would like to show the step by step. So instead of directly running it, and then we can just run, sorry, X input. I want to see this step. So I want to see this step. So we run this one step, yeah, one block at a time. So we process the spec. Now it now has two. It has now solver 8, where it then using the method of Weckstein to test stream 11 and 12. Stream 11 and 12. Stream 11 is this stream as we know it, and then stream 12 is that stream. It is by default, yeah. We can always adjust it later. So so it starts from the solver. So from this solver, it will then calculate stream 11 and 12 simultaneously. So 11 and 12 will be calculated simultaneously, and it will then start with this E2. It has been highlighted automatically. So E2 you can see. So E2, exchanger, and then the mixer, and then distillation column. So B6 is the mixer, B6 is then the valve, yeah. And the distillation columns, and then the valve distillation columns, and then vessel 1, the inlet, this inlet, vessel 1, and then pump, and then feed effluent heat exchanger, the heater, and then the reactor, splitter, and then mixer, and then uh, reactor, mixer, and then back to the solver, which calculates stream 11 and stream 12 simultaneously. And see, so this is then the default calculations done by Aspen PLUS. You can see the next step will then calculate um, the so 12, 11, and 12. It will then do that. So this is then done, I guess. So it goes this then. So all these have been done. This is also done, and then this now it's going to do vessel 1. So we run again. P1, E8, right? Everything is okay. E1, and then the reactor, and then the splitter, and then the B4, the mixer, and it goes back to the solver, and then we can run this again. E2 is then this E2. Come back, and then B6, and then A1, D1, and so on and so forth. So this will then continue. So we'll then click this run the simulation. So seems to be working very fine. Everything is converged, and then we get our results. So in this case, you have finished the simulation. Okay, I'm going to tell you a little bit more on the if you find any difficulties in converging the distillation columns, you can increase the convergence. I think the run. So it might by default it's only 25, but you can increase it to 200 if necessary. Yeah, if it's not converging. So you could see whether it will then help or not. And then the other one in the profile, which I would like to show you now. So this profile is then the profile of concentrations and temperature. So profile for each of the stages. Yeah, you can check the K values. You can check on the concentrations of vapor and liquid, and then the temperature. So we can then draw. So for example, x-axis is the stages. I want to see temperature profile. I want to see, for example, vapor or liquid or pressure. Yeah. So you can see. So temperature is then changing very fairly throughout the stages. So changing on temperature means that the separation takes place. This area is not that much, but then yeah, we can always. That means you can either remove this stage, or you can just leave it be. Another one at curve. We could then the composition. So we can look at compositions. I want to see liquid composition, small, and then I want to see all. And then you can see. So methanol coming in, right? So stage number 12, and then the methanol. All of this is coming at stage number 12 with this concentration, and then the more we go up to the stages, we will have like a pure and pure DME, and then on the bottom we have a mix of methanol and then water. So from here we can analyze, and we can see there's stream 13, 14, 15, 16, not much is happening, but okay, we can just skip it, or you can just remove these 4 stages. I think that is all that I can share for this introduction. So for more advanced course, we will see in the future. Yeah. So thank you.